Okay, so now let's move on to question 3. Question 3 in this paper, and usually would be your vertical projection question. Okay, so objects that's only experiencing the objects that's in free fall, so the object that's only experiencing gravity. Okay, so a 500-gram ball is thrown straight up into the air until it hits a concrete ceiling 5 meters above the thrower's hand. Okay, so usually just draw yourself a little picture to try and understand. So there's a ball, it's being thrown straight up into the air until it hits a concrete ceiling. So there's our concrete ceiling, and then it returns down, and this concrete ceiling is 5 meters above the thrower's hand. Okay, and then it comes down until it bounces back into the thrower's hand. First of all, define free fall. Free fall is an object in motion experiencing only gravitational force. So that's what it comes down to, an object that's only experiencing gravitational force. If it takes 0.8 seconds from the moment the ball leaves the ceiling to return to the thrower's hand, calculate at what velocity it left the ceiling. So this journey here took 0.8 seconds. Okay, so, and they're asking at what velocity, what was this initial velocity that it left there? So what do we know? Well, we only know the time it took, we know the distance that it traveled, and then we know that, and we're asked what is the initial velocity, and that's about what we know. So the information is delta x that we have, vi that we want, and delta t that we have. And also we know in this case only gravity applies. So there we go. The only formula that's got everything that we need is this one, vi delta t plus a half g delta t squared. Great, so that's 5 is equal to vi 0.8 plus a half times 9.8 times 0.8 squared. Let's put that in a calculator. So 5 minus this value. Okay, sorry, actually something that well, it doesn't really matter. They tell us use 9.8. So 9.8 means that, and sorry, this is actually very important. I forgot that. That's crucial. Sorry about forgetting that. But anyway, so 9.8 is my what is called my acceleration, and it's positive. Okay, so it's positive. In other words, acceleration is downwards, which means downwards is positive. And so that's just important so that all my time doesn't matter. Time's not a vector, it's a scalar, but all my vectors must just keep into consideration the direction. So displacement is the distance traveled, and the distance traveled, well, not the distance traveled, from where it started, from here and where it ended there. So in what direction is it? It's always also downwards. So if it was upwards, okay, so if this was asked different, in other words, if I wanted to know what was the initial velocity throwing it upwards, then it would have been -5. But this is falling downwards, so it's +5 because it is downwards, and the rest of them can stay positive. Okay, so that was just important to mention. So 5 minus, because this is going to be subtracted on the other side, minus 0.5 times 9.8 times 0.8 squared, okay, is equal to 1.865. So initial velocity is equal to 1.864 meters per second. Okay, and in what direction is it? Well, it's positive. It's a positive answer, so it's downwards. Oh, wait. I made a mistake. I'm not finished yet. Sorry, my maths is disappointing me. Okay, that's still, I forgot to divide with the 0.8. Divided by 0.8. There we go. Okay, that looks good. Initial velocity is 2,33 meters per second. Downwards. Cool? That's simple enough. Okay, next question. If it is an elastic collision that lasted 0.2 seconds, calculate the next net force that acted on the ball during the collision with the ceiling. So in other words, this time that it is in connection with the ceiling with, and I know I drew this at two different spots. It's obviously happening at the same spot here. That lasted 0.1 seconds. And they tell us that it's an elastic collision. So what does an elastic collision mean? That's important to understand. Well, it means that the kinetic energy that it hits the ceiling with and leaves the ceiling with is the same. So, well, what is its kinetic energy? Well, I can go, if I wanted to, go and calculate, well, what is the kinetic energy at this point? Half mass times velocity squared. Because I just calculated the velocity, and then this kinetic energy must be equal to the kinetic energy at that point. Okay, so the kinetic energy must equal at that point. But it's the same rest of the parameters, so it's the same mass. So basically all it means is that the velocity that it hits the ceiling with and the velocity that it leaves the ceiling with is the same. Now it's not in the same direction because kinetic energy doesn't care about direction. Kinetic energy is simply the energy that it has due to its motion, so that doesn't matter. So all it means that if during a collision where for example a ball hits a wall, if it's an elastic collision, it means the velocity that it hits the wall with and leaves the wall with is the same. If it was the collision of two different objects, then I'll have to calculate the two objects separately, etc., etc. But in this case, it simply means that the ball doesn't lose any of its velocity. No energy is lost during its collision with the wall. Okay? So then it says calculate the net force that acted on the ball during the collision with the ceiling. Okay, so which formula can account for that? Well, here we're working with a collision. The moment that we involve collisions in calculations, we should know that we're actually working with momentum. Okay, so that's the formula that's going to be used here, that net force. So what we're calculating, the net force that acted on the ball. So the net force is equal to the change in momentum over a change in time. Okay, a few formulas that you should know off by heart, definitely. And it's the change in momentum is, well, mass times change in velocity over change in time. So this is just the contact time of the collision, the change in velocity. So did the velocity change? Well, no, the velocity didn't change because it was an elastic collision. Is that true? No, the velocity did change. Okay, the velocity was initially upwards and now it is downwards. Now the magnitude didn't change, the upward magnitude and the downward magnitude didn't change, but the direction changed. So that's important. So future velocity minus initial velocity. So future velocity is downwards. So that's positive, 2,33. Okay, so mass is 0.5. 0.5. Future velocity is 2,33 minus initial velocity. Now the initial velocity is upwards. So that's minus 2,33 over change in time 0,1. Okay, so yeah, a little bit challenging question, but I don't think it's that difficult. Whenever you have a collision of an object that keeps its velocity, in other words, the velocity that it hits the wall with and leaves the wall with, so that magnitude of that velocity is the same, then the change in velocity is double that, because it changed it to 0 as it hit the wall, and then it changed it back in the opposite direction to the original velocity. So it went down all the way from that velocity to 0 to back to that velocity. So what was the change in velocity? Well, double the original velocity, and that's what we see here. It becomes 2,33 plus 2,33 times 0,5, so I'm doubling it and then halving it again, so it's just 2,33 divided by 0,5, so that's actually 23,3 newtons. Okay, in which direction? And this would be downwards. Why is it downwards? Well, it's positive. It's easy as that. Well, another question, why is it downwards? Well, because, did I ask for calculate the net force? Yes. So net force is a vector, so you have to do that. But another reason why it is downwards is because obviously it was heading upwards and it ends up going downwards. So in which direction was the net effect of all the forces? Well, downwards, because it changed velocity from upwards to downwards. Okay, how would the force that the ball exerts on the ceiling compare with the force that the ceiling exerts on the ball? State whether it will be smaller, larger, or the same, and the name of the law that informs your answer. So hopefully you know that it would be the same, and the reason why it would be the same is because of Newton's third law, that when whatever force the ball is exerting on the ceiling is exerting back on the wall. So that's Newton 3. They ask for the name, so write it out, Newton 3. Calculate the initial velocity that the ball is thrown upwards with, and then sketch a velocity versus time graph for the motion of the ball from the moment it leaves the thrower's hand until he catches it again. Okay, now here's very important, and it's really simple, so just study it, please. That there's three graphs. There is displacement, so delta x, versus time, delta x, velocity, basically future velocity graphs, and acceleration. Displacement graphs are parabolas. Velocity graphs are straight lines. Acceleration graphs are horizontal lines. If I simplify, now it could change slightly, that this can also be horizontal and these can also be straight lines, depending if it's this will be a straight line if it's traveling at a constant velocity. But if acceleration is not 0, so either this is a straight line, this is a horizontal line, and this is actually on 0, so no acceleration, then this is a horizontal line, and that's a straight line. But if acceleration is not 0, then this will be a parabola, this will be a straight line, and this will be a horizontal line, not at 0. So I say that because it was terrible, just the way people did this question. But basically it comes down to this, that we want to draw a graph, delta t, and here we go. Okay, so initially we start at some velocity and it's going upwards. So we're starting at some velocity, then it's going, the velocity is going, is being reduced, so it's upwards at some point where it hits the ceiling. Now, it doesn't get to 0, so it's not like the ball gets thrown upwards and then falls downwards, like in a usual example, where it reaches velocity of 0. So it obviously stops at some point when it hits the ceiling. From that point, it immediately goes back with the same value. Now, we know what this value is here. It is traveling at negative 2,33 the moment it hits the ceiling. At that point, then there's a 0,1 second delay, okay, 0,1 second delay where it's not moving at all. It's now hit the ceiling. That's this portion here. It's not moving at all. It's hit the ceiling, and then after that, it's immediately going downwards again. But when it's heading downwards, it's obviously now at 2,33 because the velocity is positive. And again, it's a straight line until it reaches the thrower's hand. And so this velocity here and that velocity there will also have the same magnitude but different signs. And so it's very simple, but this was just the initial velocity we had to calculate. So to calculate the initial velocity that it was thrown upwards with is, well, we know the final velocity is negative 2,33. So initial velocity is unknown. That's the velocity that we threw it upwards with. Is unknown, and that's what we try to get here, is this initial velocity. Gravity we know is 9,8. Displacement we know this time is -5 because we're moving upwards. Upwards is -5, but we don't actually need displacement, but we can use it. What else? Because obviously the time it takes to travel to the top and the time it takes to travel to the bottom is the same. But yeah, let's use what we have. So we could use the formula that future velocity squared is equal to initial velocity squared plus 2 delta xg. That one would work. So future velocity is the velocity that it hits the ceiling with. So that's negative 2,33 squared. Initial velocity is what we're trying to calculate, plus 2. Here, very important, this must be -5. -5, and g is positive 9,8. So again, why -5? Because its displacement is from here to the top. I know what the top velocity is. That's the future velocity is negative 2,33, and displacement is 5. You could have also calculated this velocity here, because as I said, the magnitude of this will be equal to the magnitude of that, and then this would have been positive 5. So in the end, you should get the same answer, even if you made this a positive. I think so. Oh yes, but this would have been then your initial velocity. These two would have swapped around then, because then you're trying to calculate future velocity. So in that case, you would have tried to get the future velocity. Notice this is future velocity, that is initial velocity. This is future velocity, that is initial velocity. So the initial velocity is equal to the future velocity in magnitude, whereas the future velocity of this first portion is equal to the initial velocity of the next portion. So they would have swapped around. In this method that we're using now, we just need to keep track of the directions. So initial velocity squared then is equal to, so it's that point, not 0.2,33 squared. You see, I didn't put in the negative because when I'm going to square it, it's going to anyway just multiply away. But it's probably best just to keep it there. Then this is going to be subtracted on the other side, but it's going to be negative already. So when it's subtracted this side, it's going to be added on the other side. So plus 2 times 5 times 9.8. Okay, that is 103,4289. So my initial velocity, if I take the square root of that, is 10,17. 10,17 meters per second upwards. Okay, so this would be 10,17. That would be the value there. Oh, negative 10,17, and up here it would be positive 10,17. And that is it. All I need to do is put in here. This is velocity in meters per second. This is time in seconds, and this is the velocity, just write a heading, velocity of ball hitting ceiling. Some sort of heading. Great. There's your 5 marks. And yeah, well, that's it. How much was this? 5, 10, 16. 16. It took me 20 minutes again with all of the explanations and the additional things. So 16 times 1.2 should take you 19 minutes anyway. So enough time to do this question as well. Wonderful. Thank you for watching. See you in question 4.